This app is very similar to the previous one, to Graasta B203. It also helps you to understand how sample mean and population mean relate to each other. But this time, it shows you how to compute a confidence interval based on sample statistics. So it means that we assume that we don't know population parameters, we compute a confidence interval, and by doing that, we estimate the population parameters. Let me explain a little bit more. Well, you can see that the configuration is more or less the same. We still have different parameters that we can change. We have population, we have sample as a set of points here. This is the population mean, and this is the sample mean, right? You can also see the sample statistics of current sample here. And now this is a little bit different. What is different? First of all, this line, in the previous app, this line shows you the sample mean, but now it shows you the population mean. And the confidence interval is based solely on the sample statistics. So it means that every time we take a new sample, the confidence interval will be a little bit different. In this case, we use t-distribution to construct confidence interval. And this is, for example, the confidence interval for the current sample. Okay. So now instead of expected sample mean, now we expect population mean to be inside the confidence interval. Okay. So let me show you an example. I take a new sample, and then you can see that the confidence interval is a little bit different now. But you can see that the estimated population mean should be within 96.9 and 106.4 with 95% confidence. And this is correct. I mean, we know that although we don't use the population parameters for computing this interval, because this is a simulation, we know that this is the population parameter, this is the population mean, and it's indeed within this confidence interval, okay? So it means that we can take a sample, even a small one like 5, and we can compute confidence interval, so with 95% confidence, the population mean will be inside. This is the overall idea, because you will almost never compute population-based confidence intervals, because you never know population parameters. Most of the time you will do it based on the sample statistics, okay? Now, what's the meaning of this 95%? It means that before you take a sample, before you take a new sample, you have 95% chance that when you compute this interval for your new sample, the true population mean will be inside this interval. Or, in other words, if you take many samples, like thousands, billions of samples, then 95% of the samples will have confidence interval with population mu inside the intervals. Okay, so let me show you an example. Let me take a lot of samples of size 5, and you can see that every time I take a new sample, the confidence interval is pretty much different. Sometimes it's more narrow, sometimes it's less narrow, because the standard deviation varies, right? You remember that this time I compute confidence interval based on the standard deviation of the sample, and it varies, of course, right? But look, in this case, I took 76 samples, and 71 of them contained the true population mean inside the confidence interval, right? So it corresponds to 93.4%. This 95%, we will see it if you keep going and, for example, take, I don't know, 70,000, then it will be 95. It will be pretty stable around 95%, but now we're already pretty close, right? So if you can just take a little bit more, you can see that the more we get, the more and more closer we have this 95%. But in reality, of course, you will never get 91 samples or 99,000 samples. You take only one, and before you do that, you have 95% chance that when you take a sample and compute confidence interval based on the sample statistics, this interval will include the population parameter inside. This is why it's very important that you decide which confidence level you work at before you actually start sampling, before you take a sample. Okay. Now let me show you again how the sigma and sample size influence this confidence intervals. It will be more or less the same as for the population based. So if, for example, the sigma is large, then the confidence interval will be also larger, because most of the samples will also have larger standard deviation, right? So you can see clearly that most of the confidence intervals also are much wider. But again, if I repeat it and take a lot of samples, you can see that most of them have this true population mu inside. And then let me just keep taking a little bit more samples. And then you can see that indeed it's approximately 95%. Once again, we will get exactly 95% if we take a lot of samples, right? And then if I get back to the original mu, let me see, 3, like this. And then, for example, take a bigger sample size. And now you see the opposite situation. Because we have a sample size is bigger, standard error is inversely proportional to square root of sample size. So we divide to square root of n. And therefore, when we have n is large, then the standard error will be small. And the most of the confidence intervals also will be smaller. But again, the idea is the same. I mean, since we use a t-distribution and it accounts for 95% confidence in this case, you can see that approximately 95% of the samples, even the sample size is large, we still have this 95% because confidence level, it's something that you defined before. It doesn't depend on the sample size, anything else. It's just that you defined, okay, if it's 95% confidence level, then 95% chance that your sample will have the true population parameter inside. Okay, so this is how it works.